So I have now done this video twice. Um, Lost both of them, sadly. And but yeah, the simulation was taking time, so I paused the video and the way I normally do, and then this one like took because I did a sweep, so it took quite a long time, and then I think the software got tired of waiting and just I don't know whether it crashed or it automatically went off, but yeah, that was it, and there was no video at the end of it when I restarted it. So I'll just, since I've already run the simulation, and so these are the results of what I wanted to show. I already run the simulation, and yeah, have the results. I would just build the model. I'll just show you how I went to about building the model through the history list, and then when it's time to run the simulation, I just show you the results instead of having to wait and run it again. Um, so yeah, always start with the Tesla cavity. So I'm still working in the same project as with last time. So I have this Tesla which has all the different tasks inside of here. So I always start with the Tesla cavity, so the vacuum, and now I want to create my spring. So I use the macro just like was shown in the previous video, and created the spiral. You can see it. What I would go to curves, and yes, so created the spiral, and then again aligned with the axis, then created the circle, and selected that, activated global, and then coordinates, then did the sweep. Wait, where is it? Yeah, I then did the sweep, and then I have so yes, so I have the spring, then I change the material to copper, and then I defined the two cylinders, the top and the bottom cylinder. So if you could see it, yes, so I defined the top and bottom cylinder, so pressure could be applied on it. So, and then after that I added the shapes, and then I moved them to the end. So I translated, so you could see translated to one end, so the left end, and then I combined the Tesla shape, because when from the parent model it's still in different parts. So if I could go back in the history tree, you see that I have many solids which you can't shell. So the solid has to be a single component for you to shell it. So I combined everything to one solid. So after the movie, I combined everything to one solid and then shelled the Tesla cavity. So that should run. Yes, so I could now click on it, and then you have a shell Tesla cavity. Then I applied niobium to it. Let's change the material to niobium, and then I mirrored the spring. Now, one thing I observed when I did the mirror was that this was okay. Yeah, you even see it. So you have an overlap of the spring, and that's because the left end cup length and the right end cup length of the Tesla cavity are not equal. So I had to translate it again, but it was later that I realized that because it wasn't meshing and it was having problems with meshing, so this overlapping region but I discovered that later. So I defined the background, so I changed the background to normal, and defined the displacement boundary condition. So the displacement boundary condition, so the first one was placed here, so the ends of the spring are fixed. So the two ends of the spring are fixed, and then you have the other end of the spring in contact with the cavity itself. So the cavity could move, but then this spring cannot move. the other end of the spring, but then the spring could also move. Then I define the traction boundary condition, which is applying the pressure. You could look at that from previous videos, applying the pressure to the surface. So I could also view the traction boundary condition so on all the cavity surface. And then define material. Okay, and then for this defined material, I changed the Young's modulus. So remember, I mentioned that we'll be controlling. Now I don't know how many things I've missed to say, but hopefully you get it. So remember, I mentioned that we would control the stiffness of the spring by changing the material properties. Now it's not physical, and copper here was just a placeholder. So I guess I can close this and look at. Okay, I can't really edit it, but then that definition was to change the Young's modulus. Okay, I could show it in this one that is already complete. So for this, I parameterize. So this is the already done model. I parameterize Young's modulus, and then you see I ran the parameter sweep. So I change it to these values to control the stiffness, which you could also approximate. Calculate using the analytic formula that you have. So yeah, then I define the parameters for the structural analysis, and I think I could show that. So again, not very detailed. It was just I didn't do any adaptive mesh. I didn't apply any non-linearity. Of course, we are not expecting large deformation, so it's just, and then the accuracy I reduced it to 1 to -6. So these were the settings I applied, and then ran the simulation. So after the first run, I got the displacement and stress and all the results you typically have. And then, oh, even now I lost the results. Oh, now that's sad. I lost the 2D, 3D results. Maybe I could. Okay. I don't think I'll run it again. I'll just show you from this one. I think I should still have the results here. Yeah. So yeah, so after the first, okay, so I tried meshing, and yes, where I moved back this other spring that I mentioned that was overlapping, so I corrected it here, and then you have no overlap again. And after the first run, I decided to just do a little bit more post-processing, which is um, evaluating the displacement along the surface, so along the surface curve, the curve defined by the surface on the surface. So, and that's what you see here. You go to modeling and curves and no peaks. Sorry, you click on pick edge, or you just press E on your keyboard, and then I picked all the edges. But then I made a mistake here. Now, just to be careful, because I also made this one in a previous video, because you have such thin walls compared to the entire structure, you could mistakenly pick the inner and the outer edge, and then you wouldn't have a result. So I made that mistake, and then I picked the wrong edge, and I would not correct that here. So I defined the curve, and then after defining the curve, I realized that I had a double edge. So because I already had a result, and if I were to delete this, I would have deleted the results. I instead created a different, I instead picked the curve again, this time correctly. So this is what I did, just so that I did not delete my results. Then I also defined the curve, and then change the material property for the sweep. Oh, I evaluated the, first of all, I evaluated the displacement for 1e to -6. So this is the displacement you have along this surface. So this is the displacement and field plot. So just put this, yeah. So this is along this line, this is the displacement that you have for Young's modulus of 1 e to power 6. Now you could calculate with the analytic formula, because like I said, although the previous video we didn't quite get some good correspondence, but I have run the analysis before and compared the numerical, detailed analysis with adaptive mesh, and like everything like really set up and got the same result. So if you are really running a detailed analysis, I would suggest that you first of all simulate the spring and then compare to the analytical results, so that from this Young's modulus you could calculate the stiffness of the spring, which corresponds to this displacement. So I have this for the first run of the result along the surface, and I wanted to show the difference and the variation of the displacement when you have different stiffness. So the stiffness is controlled by the Young's modulus. So increasing the Young's modulus increases the stiffness. And then when you look at the, okay, now how I got this result. So in the post-processing, to get the displacement, you go to post-processing and then results. Then, okay, I already have some other results here. I'll just go ahead and delete all of these. So on evaluate 2D field results, you go to evaluate on curve, and then I hope there are results here. Okay, so not 2D results yet, but I have 2D results for this. So you go to post-processing. I already have one here, but I'll just create another one, and you go to evaluate field on curve, and then you browse results. Oh, this one also doesn't, it deleted it. I have no idea why, but that's it. But then I'm sure that this one has a result. So you go to, oh, by the way, this was for the fixed fixed end. So fixed end boundary condition, this result, and I would be, oh, now I just feel that the explanation is not very okay, but I'm just doing this because this is supposed to be a two-part series, and I do not know when I would have time again to make another video. And I hope this is clear. If it is not, I guess you could comment, leave a comment in the comment section, and when I have time I would remake this video. But if not, well, then very good. So to the 3D results, you go to evaluate field on curve, and then you go to browse results. So you have from the stress, strain, displacement. So you should click on displacement and you select the magnitude, then make sure to select evaluate on curve, and then you click OK. Then you have this, and then you evaluate on curve, you have a plot like this. Now I did this for Young's modulus increasing by 1 order of magnitude, and then this is what I have. So you see that for 1 e to power 6 you have more displacement overall, and also the displacement of the ends of the Tesla cavity is also more. Than when you increase the Young's modulus, that is increasing the stiffness, you have this, and then 1 e to power 8 you have this. Now to compare with the result, because as this tends to infinity, so if you keep increasing your Young's modulus, which is increasing the stiffness, as the stiffness tends to infinity of the spring, right, you approach the fixed boundary solution. So one thing you could also do in CST is copy results. So I'm going to copy this curve and I'm going to paste it in 1D results. So I'm pasting it here. So I have results from this fixed end in this, which is stiffness, that's applying spring boundary condition. Now to compare it with this, I think, okay, I can't click and control click, so I would have to copy this also. Copy this to this folder and paste. So now I have all 4 results. So you have this for the fixed ends, then you have this for fixed ends, this for Young equal to 1 e to power 6 with a particular stiffness which you could calculate. Then you have this 7. So as this tends to infinity, your Young's modulus, which is your stiffness, as you vary to infinity, you keep approaching the fixed end boundary condition. So yeah, I think it's really cool to see. I could also log it to see if it's better. Yeah. So as this tends to infinity, you approach this profile. So that's it. You could also check it by increasing and running more sweeps to see how close we can get to the fixed end boundary condition. So that was it for the video. Apologies that yeah, I really couldn't, because after 2 videos I'm like, okay, um I really can't go another 30-40 minutes and then on this. So I hope that was clear enough. And then, of course, when you want to do your own analysis, of course, always check for convergence, refine your mesh, and make sure that you remove all sources of errors. So, yeah, that's it for this video. And yeah, till next time.